Now I am. Thank you. That's your job. About that. You can remember that every day. So we're going to go left 4. Then what? Technically. Sorry. Somebody better mark it down. We're going to follow the rules. You got it. I know you got it. Yeah, okay. So what's next? By order of operations? Okay, so we got to multiply by 1/4. What's that doing? Okay, so at this point, we've got our vertex there, and we've got another point that's right there, right? And another point that's right there. Those are kind of our key points. Whoops. So there's after one transformation. Now we're going to squish everything by 1/4. So where does this guy go? Instead of being at the point up 4, he's going to be at 1. So he's going to get squished down to there, right? And he's going to get squished down to there. And so this thing looks like that. And what's our last step? Yeah, good. We're going to go down 6. So we're going to take everything, and we'll just drag this key point, and we're going to go down 1, 2, 3, 4, 5, 6. So we end up with there, and then we were over 4 and up 1, over 4 and up 1. So that's our answer. Okay. Okay. Now we followed order of operations strictly there. Okay. Could we have? Is there any order that we could have switched of those 3 operations that wouldn't have made a difference? We could have done the multiplication first, couldn't we? Right? Everybody agree? Okay, so there's an important, and that's not an accident, there's an important relationship going on here. So in calculus, eventually in a couple of years, we'll talk about this as being an orthogonal relationship. So the vertical and the horizontal are completely disconnected. So we can deal with those completely independently, and we're going to get the same result regardless. But one thing we did notice, that when we're talking about the vertical relationships, we had to multiply before we subtracted, right? Does that make sense? So that was important. But we could have actually done the translation before or after we did the vertical multiplication. Okay? Do we get that? Which one's easier to do? I think it's probably easier to do the multiplication first, in a way, don't you think? I mean, if we did this same problem, wouldn't it be easier? I mean, to me, it just makes more sense. If we start at the origin with our parent graph, and we're going to do all the compression first and figure out what the graph looks like after it's been smushed or stretched, then all we got to do at the end is take all of the points, but we'll just take the special point, right? That's the only one we really need to track, and we'll just figure out, okay, based on the values of h and k, where's that going to go, right? In fact, if we think about it that way, you could look at this right away, and you could even say, I could compare this to a standard form for a parabola. We could say something like, what if we're going to, or not parabola, for an absolute value. If we just said, if we take an absolute value function of the form a times x minus h plus k, what do the h and k represent? The coordinates of what? The vertex, right? Everybody see that? Right? H and k, that's telling us, in terms of transformations, is telling us how far we're going to slide to the left and the right. Agreed? But if we're applying that to the special point that we call the vertex, then that's just telling us when all the dust settles after we do all our transformations, that's just telling us where the coordinates of the vertex are going to be, right? And A is just telling us, well, what's the dilation factor? Is this thing stretched or compressed vertically? Everybody get that? So we can separate those two parts, and we should always maybe do the dilation first, and then just locate the stretched or compressed graph at the right place based on the values of h and k. Okay? So let's try another one. What about with a parabola? So I'm just going to make one up here. Let's try something like g of x equals, how about, let me give you a tricky one. 2/3 times Okay, if we think about this using the same logic as before, what's my parent graph? But my parent graph, that's a transformed graph, right? But that's a transformation of what very basic, just prototype, x squared, right? So the parent graph would just be the graph f of x equals x squared, which is a what? It's going to be a parabola. Okay, so we've got a parabola. What are the three things that are being done to the parabola here? Okay, so we're squishing it because we're multiplying. How do we know we're squishing it? Because it's but so is 4/5 a fraction. It's what? Less than 1, right? So it's between 0 and 1. So when we multiply by something by a fraction between 0 and 1, we make it smaller, right? So we know that it's a compression. We're moving it left by 1, and we're moving it down by 4, right? So where are now if we think about a parabola, here's our parent graph. It goes through the point 0, 0. What are the other points? That's our special point we call the vertex. What other points does a parabola go through? 1, 1, 2, 4, etc., right? -1, 1, -2, 4. It's got that folding symmetry, right? So the vertex, what can you tell me about the vertex of that graph? Left 1 and down 4. The coordinates of the vertex are just h and k, right? So we could make this, once again, and we'll do this when we start focusing on quadratic functions even more in the future. We'll just write the standard form for we'll call this vertex form. This vertex form for a quadratic function, so I'm just going to call it v of x for vertex, equals a times the quantity x minus h squared plus k. Why do we call that vertex form? Because the vertex is located at hk, right? So the vertex is in this case, is at -1, -4, right? And what have we done to this parabola? Well, we've compressed it a little bit, right? You can look at that right away then, you can see both those transformations just right in the function itself. So what are the steps to get there? I would say let's compress it first and then slide it, okay? So maybe we need one more point here. So over 3 and up 9, so there's 5, 6, so right there. Right? So what's a convenient point to apply our dilation factor to? 3/9. And the reason being that 9 is divisible by 3, right? Okay, so if we take this point that starts off at 3/9, it's going to end up at 3/6 because 9 times 2/3 is 6, right? So it's going to slide down to there. These other ones are just going to slide in inconvenient amounts, right? Fractional amounts. But I know that on this side I'm going to get the same thing. And so I could either sketch the graph fairly well, or at least I can draw some key points, right? So I can recognize the graph. In Moodle, you're just going to have to recognize the correct graph. Right? And then last step, I'm going to take that blue graph and I'm going to move it where? Left 1, down 4. So we're just going to take this whole thing and translate it down to there. Do that right? So there it is. Oh, that was a good one. There we go. Okay. Everybody see? Okay. That's not very hard, but it does get harder. For the honors class, we're going to talk about, in addition to vertical translations, we're going to talk about horizontal compressions and translations. And then the order of operation gets a little trickier, and it gets a little, it just gets a little harder to see what the function looks like. You have to be much more careful with it. So we're not doing that today, but that's coming up. All right, so Friday, a little Friday fun. I got something for you to kind of kick off the weekend here, get you thinking a little bit.